Our webinar today will be Psychrometrics, the science of moisture in air. Today, we're going to be using a new tool that CDI is featuring. It is a Dry Tools application. This is for your phone, and you can go to your nearest app store of your choosing and download Dry Tools. It is an application that has the psychrometric calculator on it, along with the weather data as published by ASHRAE, and a few other tools that you can enjoy. So that is a phone app that is available to you, Dry Tools. Check it out. Well, welcome from sunny southern Minnesota. This is Tom Peterson, Dr. Dry from Climate by Design International. We are your manufacturer for desiccant-based dehumidification systems and air handlers along for critical process environments. A couple of things that you should know today. You are on mute. There's enough folks joining us today that we have muted you. If you have a question, please use the question drop-down menu off the Go to Webinar menu and type your question in, and we will get that and answer it as we go or at the end of this webinar, time allowing. So please post your questions via the question box. Today you'll also notice that there are handouts. Those handouts include a PDF of the Psychrometric Chart in two versions, IP and SI. So download those if you wish, as well as the PowerPoint presentation itself in the handouts section of the Go to Webinar drop-down menu. So welcome today to Psychrometrics, the science of moisture in air. Our webinar today will be 45 minutes long, followed up by any questions that you might have. So our subject, psychrometrics or psychrometry. It is the field of engineering where we concern ourselves with the determination of the physical and thermodynamic properties of a gas-vapor mixture. And today it's the one that we breathe in and out every day. This is the psychrometric chart we're going to be using, and look at all those lines. We're going to break down those lines one by one, but this is a graphical representation of air that, again, we breathe in and out every day. There are other psychrometric charts for other gas vapor mixtures, but this is the one we're using. And we're going to be using the chart at sea level. It does change as you would change altitude or barometric pressure. So this one's at altitude. And we're going to break these lines down one by one so you can use this as a tool to understand moisture in air. And we're going to start out with the one that you know the most, dry bulb temperature. That is the temperature of air measured by a thermometer. It's freely exposed to the air, but it's going to be shielded from radiation and moisture. So that thermometer that's sitting outside your home, but shielded from radiation. What is dry bulb? Or why do we use dry bulb? I'll state that again. Why do we use dry bulb? Dry bulb is what most of us see on the thermometer, and it's our best point of reference. On our psychrometric chart, you'll notice down at the bottom, dry bulb temperature, and you'll see the numbers. And we can start at the left here, which is approximately 0, and follow it all the way over to the right. The temperatures go up as we move to the right. The dry bulb temperature, and let's just put a point here. If I follow that straight down, I will see that it lines up with 63 degrees Fahrenheit. 63 degrees Fahrenheit. So anything along that line, whether it's way down here at the bottom or way up at the top, anything along that line would be 63 degrees dry bulb. We're going to move our conversation to moisture in air. H2O, 2 hydrogens, 1 oxygen. It's nothing but a vapor as we see it in air. The most common moisture measurement that we relate to or hear the most is probably relative humidity. It is a percentage of saturation at any given temperature. It's always going to be relative to a temperature. So if we are talking to someone and they say, I have an application and it's 50% relative humidity. That's my target. Well, that's going to raise questions because we don't have the corresponding condition. We need to have a corresponding condition. Dry bulb would be most normal. And so let's say that they're going to tell us it's 70 degrees dry bulb temperature. So now we have a corresponding condition. We can understand how much moisture is in the air and our questions can go away. So relative humidity is relative to a temperature condition. Why do we use relative humidity? Primarily it's because what we feel. We give up moisture through evaporation on our bodies, and we're more in tune with this thing called relative humidity, or the surroundings air ability to take on moisture as it would evaporate from our bodies. So if you're in Arizona and the temperature is 90 degrees, but the relative humidity is down around 20%, as compared to Minnesota in the summertime where it's maybe a cooler temperature, let's say 80 degrees, but now it's 60% relative humidity. In the Arizona condition, drier, we're going to give up that evaporated moisture from our bodies more easily and therefore feel cooler compared to the Minnesota condition where it just feels quite hot and sweaty. So relative humidity is what you feel. Now, there are other reasons that we look at relative humidity because things start to happen as we approach 100% relative humidity, things like fog and condensation. There are some applications as well that we need to know relative humidity. For instance, in archival storage of a metal where it starts to corrode at 30% relative humidity no matter what the temperature. So there are other reasons to look at relative humidity. On our psychrometric chart, the relative humidity lines, or the RH lines, are these curved lines. And you can see them as we go through until you get to the final one, which is 100% relative humidity. It is at that point full of moisture, it can hold no more. In the example off to the right, we're showing something that says 50% relative humidity. And we're showing a bucket here, if you will, that's half full. The point we're trying to make is that at 50% relative humidity, the moisture in that bucket of air can be increased by the equal amount to get up to 100% saturation or 100% relative humidity. Let's look at it another way on this chart. What we're trying to communicate is that when we take a bucket of air, a CFM if you will, a cubic foot, 12 inches by 12 inches by 12 inches, and when we increase the temperature, we're going to expand that. So the far left condition is 45 degrees saturated, 45 degrees at 100% relative humidity, if you will. So if we take that bucket of air and we warm it up, moving it to the right, now we're not changing the moisture condition, we're just warming up the air. As we do that, the relative humidity goes down. The second condition is 70 degrees and 40% relative humidity. We keep warming that air up to this third condition, which is 90 degrees and 20% relative humidity. The actual amount of moisture is not changing as we do that, but the relative humidity is changing significantly. See how much more moisture that can be held as we warm this bucket of air up or take that CFM and expand it. So the warmer it is, the more moisture it can hold, and it's really an exponential growth curve of how much moisture can be held. Wet bulb temperature, what is it? Well, now we're starting to talk about measuring moisture or humidity, and this is going to be expressed in the terms of the instrument that was used to measure it. This instrument, the sling psychrometer, relies on the evaporative cooling effect. It is a temperature-dependent humidity measurement. So the device that is used to measure wet bulb is the sling psychrometer. It does have a dry bulb thermometer on it, as we can see here, at least hopefully you can see that. There's the dry bulb. But it also has a second thermometer that has a little cotton sock on it. We wet that sock and then we start to rotate as fast as we can the psychrometer. so that the evaporative cooling effect drops the temperature on the wetted surface, on the second or the wet bulb thermometer, until the point of saturation. So why do we use wet bulb? Who has a sling psychrometer in their back pocket? Probably no one. I have one. But why do we use wet bulb? Well, wet bulb really became the first recognized and accepted and used, and still is, for communicating moisture and air. Quite often when we're looking at a cooling coil program or something like that, we're going to be asked for a dry bulb and a wet bulb condition. Wet bulb lines are diagonal lines on your psychrometric chart. These wet bulb lines, and I'm going to help you just a little bit. I'm going to zoom in. Let's try that anyway. So as you zoom in, you can identify and read, hopefully, these lines where the one here says wet bulb temperature. So everything parallel to that are going to be wet bulb temperature lines. They are diagonal lines on the psychrometric chart. Again, any point on that line, that would be a wet bulb temperature anywhere on the line. So you can see that because it's a diagonal line, at this dry bulb temperature, we have a wet bulb that's on this line, but it's the same wet bulb even when the temperature would increase. Anything on that line is the same wet bulb temperature. It is a temperature dependent number. Let's discuss enthalpy or enthalpy. A specific enthalpy is the sum of the internal heat energy of the moisture in air in question. It's both the heat of the air and the water vapor within. And enthalpy is going to be discussed or used in terms of BTUs per pound of dry air. Pound of dry air. Why do we use enthalpy? So that we can determine energy required to change states. Enthalpy is also a diagonal line, and they're very close to the wet bulb line. So be careful as you would look at the chart. We help you out by having the enthalpy listed on the two edges, where then you can take a straight line, my line not very straight there, sorry about that, from one to the other and find any point along that line. So again, any point on that line is going to be the same enthalpy. Let's take a look at an example of determining an energy amount required. And our example today, we're going to be using 13,000, count them, 13,500. I'm going to add this for you, SCFM. We have abbreviated it CFM, and that's fairly common, that we have a lot of abbreviations when we're discussing these things amongst ourselves. But this is SCFM, standard air, 70 degrees, 50% relative humidity at sea level. So 13,500 CFM. Why did I want to call that out to you? Because we're using a constant here of 4.5. 4.5 times 13,500 CFM, the change in enthalpy. So this higher condition, and if I'll try to follow the line up here for you, this higher condition has an enthalpy of 41.46. This lower condition has an enthalpy of 23.18. And so the difference of those two times the amount of air that we have times the constant of 4.5 is going to tell us how much energy is going to be applied to that airstream in BTUs per hour to go from the higher enthalpy condition to the lower enthalpy condition. Enthalpy, it's used to help you determine how much heating and or cooling we are doing. We noticed that enthalpy was so many BTUs per pound of dry air. So how can we know how many pounds of dry air we have? Let's discuss air density. It's going to be measured in quantity of cubic feet to make up a pound. How many cubic feet does it take to make up 1 pound? Why are we concerned with density? Because ultimately we want to know the mass of the air volume, and we need to know that mass to run our calculations. We generally know the CFM of a system. That's become our normal means of discussing volumes because we're using fan air movers and distribution, ductwork, and that sort of thing. So our normal conversation is around CFM. But in order to understand the heat and dehumidification required, we really need to understand the mass of the air. So we have an example for you today. Our example is how many pounds of dry air are moved on a 13,500 CFM SCFM fan system. We'll take a look at our psychrometric chart, find the foot cube per pound, take our SCFM, divide it by the foot cube per pound, and we'll come up with pounds per minute. So 13,500 CFM divided by what? Let's look at our chart. These are going to be, again, diagonal lines. What we're trying to solve for is how many cubic footsies does it take to equal 1 pound. In our example, we are going to come up the 70-degree line, 70 degrees dry bulb, straight up. We're going to cross over the 50% RH, and you will see then that we're right on this blue line, which is 13.5 cubic foot per pound. Why did I choose that example? Because I'm not very good at math. 13,500 SCFM. 13,500 SCFM divided by 13.5. We're going to be moving 1,000 pounds in a minute of air. So just to give you some relative thoughts, if you had 1,000 pounds of bricks in your backyard and you were going to move them in 1 minute, you can see how much energy that requires. And so a 13,500 SCFM fan system that requires 10 horsepower, that'll give you some kind of idea of, what kind of work you're actually doing. We're moving 1,000 pounds per minute of dry air in this example. Let's move on to talk about the absolute humidity measurements. These are going to be irrespective of temperature. We want to have an expression of moisture content irrespective of temperature. The three we're looking at today: dew point, number one, the ratio of weight of water to the weight of the air, and then vapor pressure in inches of mercury. 3 measurements of absolute humidity. Starting with dew point. Dew point is the temperature to which air must be cooled for the dew to drop out or for condensation to occur. Many of our dehumidification applications are dew point applications. If you have a food processing facility and it has a 38-degree chill water pipe running through the ceiling, running above your processing equipment, you have to control to something below that temperature, or else the dew will fall out and potentially get into the process. That is one example. So dew point is where the dew falls out. Why does that happen? We said earlier that as you heat air, that bucket of air, if you will, expands and can hold more moisture. Well, when we cool it, the opposite happens. That bucket of air gets smaller, and as it moves toward the 100% saturation line, let's use this one down here, anything along that line, this one in particular is a 45-degree dew point. We keep following it over until we get to the 100%. So that is where the dew falls out, or we get to that 45-degree dew point. To know what that number is, again, it's a horizontal line, and you follow it across to the right, and here you can see dew point temperature. So any line that is horizontal on our psychrometric chart, and I'm sorry I'm not drawing very good horizontal lines here, any line that's horizontal on our psychrometric chart is going to be a measurement of moisture irrespective of temperature. So dew point is one that we use quite frequently. The ratio, the weight ratio of water to air, this is the most common used term in moisture calculations. It is a ratio of weight of the water to the air. We could use pounds of water per pound of dry air, but the number gets too small. It's 0.007 or some small number that's hard to remember and hard to use. And so instead, we use a different measurement of weight for the water. We use grains. What is a grain? Well, there's 7,000 of them in a pound of water. So a grain is 1/7,000th of a pound. 7,000 grains equals 1 pound. To give you some idea of how much water that would represent, an average, if there is such a thing, an average drop of water weighs about 4 grains. So if you had 1 drop of water in your palm of your hand, that would be about 4 grains of weight. On our psychrometric chart, again, the horizontal lines coming across, and if I were to draw a line here, go through the 60 grain, and you can see the grains of moisture per pound of dry air, the words there. So that's 60 grains of moisture per pound of dry air. So if we had that 13.5 cubic feet equaling 1 pound, in 13.5 cubic feet of air, you'd have 60 grains of moisture, which would be like 15 drops, if you can think of it. So it'll give you some kind of an idea of how much moisture that a grain is. So humidity ratio, grains of moisture per pound of dry air. The next one, vapor pressure. It is going to describe that partial, or that part of pressure of the moisture in air. Now, this one is important because this is the motive force that drives water vapor from high to low. Which way does it go? From high to low. One way I remember it is to think about throwing a bucket of water up in the air. Which way does it go? High to low. Well, that's actually gravity, but moisture and anything, pressure, is going to move from high to low. Anything pressure related is going to move high to low. So vapor pressure, that partial pressure of moisture in air, is going to move from high to low. Let's take a look at an example that would help you understand the significant force that vapor pressure is. Let's say that we want to control a building interior to 65 degrees Fahrenheit and 10 grains. That might be some sort of archival storage or some such system. Let's put this building in Atlanta, where the summer design ambient condition is 82 degrees dry bulb and 74 dew point. Let's ask ourselves the question, can you eliminate moisture infiltration by pressurizing the room? Or ask the question a different way, to what level would we have to raise the room pressure to stop moisture infiltration? Well, this is a pressure question, so we're going to look for the vapor pressure of these two conditions. The outdoor condition here, 82 degrees and 74 wet bulb, has a corresponding vapor pressure of 0.847 inches of mercury. Now, our fan systems that we deal with are using inches of water column. So 0.847 times 13.6, we will see that that pressure, that partial pressure of the moisture in the air, is 11.5 inches of water column. Very significant. Compare that to the indoor design condition. That condition only has a vapor pressure of let's call it 0.07, so somewhere around an inch. So the difference between these two, 11.5 inches of water column versus 1 inch of water column, we would have to pressurize that room to over 10 inches of water column pressure in order to overcome the vapor pressure. So can we pressurize a room that high? No, we can't. We normally pressurize a room to something in the neighborhood of 0.02, 0.05, maybe 0.1 inches at the very most. So why do we pressurize the rooms? We pressurize the rooms so that the air volume itself, the cubic feet of air, do not come into the room and therefore bringing in more moisture with so many cubic footsies of air. We do not pressurize to try to stop or overcome vapor pressure. It just cannot be done. Let's look at a little example here. Let's take a building, and for this example, our building is going to be 100% sealed. It's a tin can, if you will. So our outdoor condition of 135 grains is not having an impact on this supposed example. But the two indoor conditions, let's hold this side at 75 degrees, 50% relative humidity. The other side at 62 degrees and 50% relative humidity. This would be similar to a hospital operating suite. corresponding grains 65 and 41, corresponding vapor pressure 0.438 and 0.28. So this side of the room that has the higher pressure, that moisture is going to want to move right through the walls if it can permeate the walls. If these are sheetrock walls, there's no vapor barrier, it's cement walls, that moisture is going to move through. It's going to permeate through the wall. Or if there are cracks around doors or the door is opened, then we are going to want to equalize this pressure. In this case, if we left the door open and we didn't do anything else about it, it's going to equalize at about 0.34 inches of mercury. So vapor pressure moves from high to low, very significant force. We talked now about 3 different absolute measurements of moisture. Why do we use absolute measurements of moisture? Because the formulas or the calculations that we need to perform use those conditions. So for instance, moisture capacity. If we have a system that is of some known CFM, and again SCFM, we use the constant of 4.5 and look at the grains in versus the grains out, and that will tell us how much work that system can do or is doing. Permeation, we just breezed on there just a little bit. We take the area of the wall and then the vapor pressure differential from the inside out, and then the permeability of that wall. For instance, a wood wall is more permeable than cement. So different permeance factors for different materials, but we can determine how much moisture will move right through the walls. Evaporation, again, we need to know the vapor pressure of the air compared to vapor pressure of the water, and so on, so we can determine evaporation. So those are just a couple of examples of why we need absolute humidity measurements. To recap, you're going to find them on the right-hand side of the psychrometric chart. They are horizontal lines. They do not change with temperature increase or decrease, assuming that we don't get to the line of condensation. We use humidity ratio. It is a ratio of weight, in this case grains, of moisture to pounds of dry air. Dew point, at which point the dew falls out, and vapor pressure, that partial pressure of moisture in air. Well, have you noticed yet that if we know any 2 parameters of the condition of the air, we can identify all the rest? Let's start at the bottom of our chart again with dry bulb temperature. Let's follow up the 70-degree line. As we would cut through 50% relative humidity, we come to a point. We knew those 2 conditions, 70 degrees, 50% RH. Now that we know that, we can come over to the right horizontally and we can find any one of the 3 absolute measurements of moisture, grains per pound, vapor pressure, or dew point. We can follow the enthalpy line and find the enthalpy of that condition. We can find out how many cubic feet of air that is per pound. Any 2 conditions, we can find all the rest. This is where our phone app can help you. Please check that out. You can download that from your favorite app store. The CDI Dry Tools app for your phone. So we've been talking about psychrometrics, and there is a psychrometric calculator available on this app. Looks something like this on the right-hand side of your screen. Again, any 2 points identify all others. So if we type in the ones we know, in this case 63 degrees, and then a wet bulb of 49.74, it gives us all the other conditions: relative humidity, the humidity ratio in grains per pound, dew point, and vapor pressure, and so on. So that is the phone app. It is free. You can download it on any app store. We're going to be talking about some other software here in just a minute, but I want to differentiate between this one, which is a phone app and has the psychrometric calculator on it, as well as the ambient outdoor conditions from the ASHRAE database. So in our next example, we're going to look at the 2 different published conditions, 0.4% cooling and 0.4% dehumidification for a specific example, and let's use Charleston, South Carolina. So going back to our app, we can look up Charleston, South Carolina, and it's going to give us the ASHRAE data for these two conditions. So the high dry bulb or the cooling design condition, 0.4% of the time, it is going to be better than this, 94.3 degrees, 120 grains. If we look at the dehumidification or the high humidity condition, 0.4%, notice that the dry bulb temperature is lower, 84. It's 10 degrees lower, but look at the water. It's going up now to 147 grains per pound. So two good conditions, 94, 120, 84, 147. Let's go ahead and plot that on our chart. Here's the 84 degrees, it's cooler, follow that up, 84, come over from the 147 grains, that's our point. And the high dry bulb condition, we follow up the dry bulb line, we come over grains of moisture, we find that second point. Why are we doing this? We want to understand which condition is going to require more energy, which is the safer condition to design to for a dehumidification application. And if we now then look at the enthalpy of those two conditions, we're going to see that the enthalpy of the higher condition of the moisture condition has a higher enthalpy. This came from the example we saw earlier, 13,500 CFM, up there at 41.46 BTUs per pound. That's the enthalpy. So we would suggest that when you take a look at the data, you then look at the psychrometric chart, determine which one you should use based on the higher level of energy required to make sure you provide enough dehumidification. Let's move on to psychrometric processes. These are going to be changes in temperature and or moisture content, and they can be described on the psychrometric chart, such as multiple blended air streams. They're going to be shown as process lines. We can show relative volumes. Now remember, these process lines must obey the rules that describe the specific processes. So let's go ahead and look at these processes, remembering that energy goes from hot to cold. Any changes to the left or the right on the psychrometric chart is going to change temperature. Moisture is going to go from the high moisture condition to dry. Remember, we talked about vapor pressure. So the wetter it is, the higher vapor pressure it is. So that moisture is going to move from wet to dry. Any changes up or down on our psychrometric chart are going to change the moisture condition. There is a perfect temperature-moisture exchange, and that is called a constant enthalpy process. We're going to look at one of those today. Let's start with sensible heating. So if I have this point on the left and I add heat, indirect heat to this, electric heat, some kind of hot water coil, something that's not changing the moisture content. If I add heat to this, as we expand the air, we're coming over to the right and sensibly heating it. If we're going to do the reverse, we're going to take this point and cool it. As long as we don't get to this 100% line, all of that cooling is sensible as well. So sensible heating and cooling, it's going to follow a horizontal line. It's not going to go up, it's not going to go down, because we're not doing anything with the moisture, speaking of sensible heating or cooling. Contrast that with latent cooling, where now we start at a point and our cooling coil drives that temperature down to the 100% relative humidity, or the saturation point, where now the dew starts to fall out, and then we bring that down to some other given condition that is going to be more or less saturated. Latent cooling. That perfect temperature moisture exchange that we talked about, evaporative cooling. If we start at this condition of 0.1 and we evaporate moisture into that airstream that's roughly the same temperature as the airstream, we will have a constant enthalpy process. It will reduce the temperature, moving to the left. It will increase the moisture in the air, moving up, along the enthalpy line. And in the case of an evaporative cooler, it's going to move it as a percentage of the efficiency of the evaporative cooler. So this one, not coming all the way to the point of saturation. It looks to me like it's about a 75% efficient evaporative cooler that we're demonstrating in this example. So that's evaporative cooling. Desiccant dehumidification, if the desiccant had no mass, it would do the same thing. It would follow the enthalpy line down. But because it has mass, there's some heat carryover, some sensible heat carryover, so that pushes it out to the right. So that's what desiccant dehumidification looks like on a psychrometric chart. We can combine processes and describe them on our chart. This is a very common application for us where we take outside air, we pre-cool it with some sort of a cooling coil, DX or chill water, whatever it might be, to get a lot of water out of the system on those really high moisture days. You can see there's quite a bit of water being removed. That's not dry enough yet, so we now go through the desiccant dehumidifier, bringing that down the enthalpy line, kicking it out a little bit to the right. And that temperature now is generally in the 80 degree range, 85, something like that. Might be 90, 95 even. That's too warm for the room, so we're going to sensibly post-cool it. No more moisture coming out. And matter of fact, in this case, if we kept moving off to the right, we'd be way down there at a 20 degree dew point or something quite low. So combined processes. This one is latent cooling, desiccant dehumidification, and sensible post-cooling. Another thing we can do is show two sides of the same process. So this one, again, desiccant dehumidification. This is the side, the process side, or the side of the system where we're removing moisture. On the top, this is the reactivation. This is where the water is being expelled from the system back into the atmosphere. I wanted to give you this example because it's an example of the relative lengths of a line give you relative volumes. So this example, let's say that we have 9,000 CFM of air that we're going to dehumidify, 9,000 CFM. That energy that's shown in this process line, the same exact amount of energy is in this process line. Why is this line then 3 times longer? Well, it is because it is 1/3 of the air. If this is 9,000 CFM on the process side, we have roughly 3,000 CFM on the reactivation side. So it is 1/3 of the air. So the same amount of energy will give us a line that's 3 times longer on our chart. So you can look at relative volumes. Our next example is an enthalpy heat recovery process. We take a return condition, 70 degrees and 50% relative humidity, let's say, and as that return air goes through this enthalpy heat recovery exchanger, it's going to pick up the moisture, it's going to pick up the heat of the outdoor air, which is coming across the other side. Now again, these two lines are equal because one side has to equal the other side unless you're getting in some kind of purge or something. And you can also see that the exhaust air condition approaches but can never get to the outdoor air condition. The difference then is the efficiency of that heat exchanger, this one being about 80% efficient. So you can show both sides of a process. We just saw two examples in the desiccant dehumidification and the enthalpy heat recovery. Let's move on now and talk about air mixing. Air mixing can be shown on our chart. If we have outside air at this condition, return air at this condition, and we are told we're 20% outside air, We can draw a line from the outside air to the return air, come back 20% of the distance because it has 20% of the effect, and that will give us our mixed air condition. So we can show air mixing on the psychrometric chart. We can show control conditions. Let's say someone wants us to control to 70 degrees plus or minus 5 degrees and 40% plus or minus 2% RH. Let's show that on the psychrometric chart. And one reason we might want to show that is because that's a very tight band when it comes to moisture at any given temperature. At any given temperature, it's a tight band. So from, let's say we're controlling right at 70 degrees, there's not a lot of room for error, and so our control system is going to have to be quite precise on the moisture side of the equation. Not so much maybe on the dry bulb side or on the temperature side. We've got a lot of swing there. So this might be a situation where we want to go back and talk to our customer and say, well, you know, maybe we should look at a tighter dry bulb condition and a looser relative humidity condition, and so that the controls don't get too expensive. So control conditions can be shown. Another one that's quite frequently done is the hospital operating suite. AIA talks about 68 degrees, 50% RH as a kind of a standard. So it's actually a range from 30% up to 60%. However, they also go on to say that whatever the surgeon desires is what needs to happen. And so by practical experience, we know that in a lot of cases they're asking us to get down to 62 degrees. So let's show that on a psychrometric chart so that we can help them understand what they're asking for. One last line on the chart I'd like to talk about is the sensible to total heat ratio line. This line, in order to know what this line is, you have to know your sensible load of the room and your total load, or sensible plus latent to get to total. It is a heat ratio. So sensible being just a part of the load, that means this ratio is always going to be below 1. If we have a heat ratio that is quite high or close to 1, that means that the load is mostly sensible. It helps us understand maybe what the system might be. However, if we go the other way and we have a ratio that gets down into the lower numbers, that tells us that we have a large latent or moisture component that we have to deal with. Here's a real example that we were asked to do. The room was to be held at 45 degrees and 80% relative humidity. The outside air was way up here somewhere. 5% outside air, that gave us a mixed air condition in this case, and then we were post-cooling. We're going to drill into this just a little bit closer. We were given an ammonia system that we could come off of a coil at 35 degrees. That's as cool as we could get with that available system. So at 35 degrees, we were to control this room. However, when we put the sensible to total heat ratio line on here, you can see that we are not getting to the line. Or let me state it differently. Let me just go back and erase this, these lines. Okay, we've got a clean screen. So we've taken the desired condition, which is 45 degrees and 80% relative humidity, and that's the desired control condition. Through that control condition, we have drawn the sensible to total heat ratio line. What that sensible total heat ratio line describes for us is anything on that line we need to provide air at that condition, so as it goes through the room and it takes on the heat moving to the right, it takes on the moisture moving up, we end at the control condition. The farther we are away from the point, the less air that it takes. The closer we are to the point, the more air that it takes to do that. So sensible to total heat ratio lines can really help us understand a system. In this case, we can see that with the cooling coil provided, we can't get there with just cooling. We're going to need to move to some sort of cooling and desiccant dehumidification system to get to that condition. I'd like to introduce to you now the second tool that we have, and now this is your desktop application or laptop application. This is our psychrometric tool. And all the psychrometric charts that you've seen today came off of this tool. And there's a lot of things that you can do with this tool. You can map out the entire flow of a system and see how the energy is used. You can apply bin data. So in this example, we went back to Charleston, South Carolina, and for just the month of November, so I'm showing you here just the month of November, and this is 7 days a week and 24 hours a day. These are the conditions of the air during that month, during that season. So you can pick and choose hours of the day and so on. What is that for? That helps you, again, visually to understand what's happening with the outside air so that you can design your system. So that's the second tool that I wanted to talk to you about today. That is available to you free of charge. And we've run a few minutes over, but if you do have questions, we'd like to take those at this time. While I'm waiting for you to type in questions, please complete our survey at the end of this webinar. Check out our website. There's lots of information there. We will send you some free laminated psychrometric charts if you want that. The Psychrometric desktop chart software, normally $299 retail, is free for you putting up with all my verbal mistakes today. Just let us know at that survey, if you will, and if you would like that, we can send that to you. PowerPoints of the session, as I described earlier, and the PDFs of the psychrometric chart you can download off of the handouts page of the GoToWebinar. Professional development hours, if you want those, we can get those to you. You can contact us at drdry@cdihvac.com. The second tool we talked about today is a phone application. Go to your nearest app store and look for Dry Tools. Contact information, drdry@cdihvac.com. There's our website. Thanks Scott Lindberg, Johnny Peterson, Sean Turek for our illustrations today. This is Dr. Dry from CDI, Climate by Design International. We are your manufacturer for desiccant-based dehumidification equipment, along with air handlers for critical process environments. Thank you for joining us today.